All right, so we're going to go ahead and get started with this lesson 603. In this lesson, we're going to introduce to you guys a new irrational number, which we will be applying to solve exponential problems involving compound interest, especially compound continuous interest, which we'll talk about in just a second. So in front of you, you should have your packet open to page 10. Let's go over the partner investigation. I'm going to set it up for you guys so that you know what I expect from you, and I'll tell you what to do in just a second. Now, before we jump into this, I do want to remind you of the following. So last week we explored compound interest, and we talked about this idea that anytime the bank counts how much interest you have with your money, that's a compound event. So we talked about this, that the more often the bank compounds the interest, the more money that you will get. It makes sense, right? Because each time that you're compounding the interest, you're adding more and more interest on top. Now, in this investigation, we are going to see what happens if we were to compound so many times. Would our money then increase forever and ever? Would there be a limit? Would it stop? So that is the idea that we're trying to get to, or that we're trying to get you guys to see. Now, listen to the following scenario. Suppose you deposit $1 in the bank, and this bank offers you 100% annual interest. If you were to leave your money in the bank for a year, how much money would you expect to get out, depending on the following? If it's compounded annually, semi-annually, etc., etc., etc. Now, before we get there, let's just fill in the following variables. Now, capital P stands for principal. Principal is your initial investment. What would the principal be for the scenario that we were just posed with? 1. So we are starting with $1. Now, the rate of interest, the interest rate, essentially, is 100%. However, we don't want to leave things in terms of percentages. We want to convert percentages to decimals. So what would 100% become? What would it be? It would be 1, right? Anything greater than 100% is going to be a whole number. So something like 120% translates to 1.2. 200% translates to 2 as a whole number, okay? All right, and lastly, T stands for time. We're leaving the money in the bank for how much time? 1 year, okay? So we're going to go ahead and we're going to default all of these variables to 1. And so what that's going to allow us to do is it's going to let us replace those corresponding variables in this formula down here. For example, A of t, this formula here, will become the following. Please write this down. A of t will become 1 parentheses 1 plus 1 over n to the n. Now, if you look closely, what happened here was the principal became 1, the rate became a 1, and then time became a 1, but I didn't include it because if I'm multiplying n times 1, I could just write it as n. Now, the only thing that was left without changing was this variable n. And what does this variable n represent? Yeah, my drawer over there. What does the variable n represent? So we know P stands for principal, we know R stands for rate, T stands for time, N stands for what? Think about it. What does N stand for? What is the idea that we're looking at? What is the name of the last lesson that we looked at? It was what? What interest? What's that word? C. Let's start with the C. Compound. So N is the number of times that you're compounding the interest. That is what N represents. So let's go ahead and look at the following. We want to see what happens if the interest is compounded more and more often. How much money will you have after a year if the interest is compounded? We're going to fill in the following. If something takes place annually, how many times a year do you expect something to happen? If it's annually, we should expect it 1 time a year. If it's semi-annually, we should expect it how many times? 2 times a year. If it's quarterly, 4. Monthly, 12. There are 12 months in a year. If it's daily, how many days in a year? 365. Now, we already filled this part out in the last lesson, but every minute, how many minutes are there in a whole year? If you're not sure, go back to page number 7, I believe it was. 525,000, right? 600. Now, this is a new one. Let's say that we were to compound the interest every second. So now, how much would that be? Well, to find out, you're going to take this quantity of 525,000 and you're going to multiply this by 60. And the reason why is because there are 60 seconds in a minute. So at this time, in your calculator, type in 525,600 times 60. And when you have it, raise your hand so that we can write it down. Santiago, go ahead. 31,536,000. Okay. Now this is where the computational aspect of this warm-up goes in here. So you should have a calculator in front of you. I'm going to show you guys what I'm looking for. I'm going to do this once, and then you're going to do the rest. I'm just going to set it up for you guys so that you know what to expect. But what we're going to do next is the following. Okay. So we said the equation is 1 parentheses 1 plus 1 divided by n. Now, in the scenario where we have annual compounding, how many times a year did we say that was? It was once a year. So we have the following. 1 parentheses 1 plus 1 divided by 1 to the 1 power. So the balance in the bank after 1 year, assuming that it's compounded annually, we should expect to have $2. Okay? So let's go back to this part, and you're going to write in $2. Okay? I'll do one more with you guys, and then I'll have you guys do it on your own. Thank you. Okay, so let's do the next one, which is semi-annually. So we go back to the calculator. We're going to go 1 parentheses 1 plus 1 divided by, in this case, because it's semi-annual, now it's going to be n equals 2. So divided by 2 to the 2nd power. So if we compound the interest twice a year, then the balance will be $2.25. Yep. Let's go back and write that down. $2.25. Okay, you're going to repeat these steps in the calculator, but you're going to replace n with whatever the value for n is in that line. So for quarterly, replace n with a 4 and write out your answer. Then go to monthly, replace n with a 12 and write out your answer. Does that make sense? So you're plugging these values of n into this equation right here. This is where you're putting the calculator. Make sense? I'm going to give you guys 3 minutes. You can do this with your partner or by yourself. For your solutions, do not round it. I want it 4 decimal places. I'll write it up here on the board. 4 decimal places. So if it's something like this, 5.12345, you're stopping at the 4th place. Don't round it. Just stop there. Does that make sense? Okay. So at this time, take 3 minutes to go ahead and take care of that. All right. So what will the balance be if we compound the interest quarterly? Let me hear from Jonathan Hernandez. 2.441. Okay. What about if we compound the interest monthly? Then how much money can we expect? Let me hear from Santiago. 2.6130. And if we continue to compound it even more, let's talk about daily. So with daily compounding, how much money can we expect? Leilani? 2.7145. Now look at the difference between daily and every minute. We're going from 300 and something to like 525,000. That's a lot. That's a lot of more compounding that we're doing here. But let's see what happens to the balance. Adrian, what do we get for compounding every minute? Mm-hmm. What else do we get after that? 2.71. I'm not sure if there's a 4 after that. 2.71882, right? 82. Okay. Now let's say that I'll give you your test. Oh yeah. Okay, I'll get you one right now. Let me finish this. Now let's look at every second. Now we're going from 500,000 to 31 million. But what is the balance after compounding that much? What can we expect? Seth, what can we expect? The same number, 2.7182. Now, what I want you to do at this time is I want you to write something down for the following. What do you notice is happening to the balance as we increase the amount of times that we compound the interest? Does it grow forever, or does it reach a limit? Does it stop growing? And if it stops growing, I want you to tell me to what number we are getting close to, or what number seems to be that asymptote, that limit, the one that we get to, but we cannot get any higher than that. So let's do the following. Take a minute to write something down, and then we'll do a class discussion. All right, go ahead and do that at this time. Okay. So let me get some of you guys to kind of tell me what your partner said or what you said. Starting with DeMarco. I'm sorry, DeMarco. There seems to be other people that don't respect. Go ahead. The whole number is 2. Okay. So yeah, so we notice that it's a 2. And it starts with a 2, but here's the question. Do we ever get to 3? It doesn't look like we get to 3. Now, we could try to find out what the balance would be if we went for every nanosecond and then getting smaller and smaller and smaller, but I don't think that we will ever get to 3. Now, more importantly is the following. What do we notice for these two numbers here? Are they the same? Yes. So what I wanted you guys to kind of think about is it doesn't matter how much more we start to compound the interest, there eventually will be a what? A limit. We will not be able to get higher than 2.7182. Now, we're going to go to the guided notes. And let's write the following. So this table shows that if the number of times that we increase the the number of times that we compound the interest increases, that's what n represents, the number of times we compound the interest, then the balance after a year will also increase. Seems only, right. The balance will increase if the compounding events increase. But there is a limit to how much it will increase. And so that's kind of what we explored right now, is that the money will not grow forever and ever into infinity. No. It will hit a limit. It will not get bigger than this value. Now, this limit does have a name. It is a number, and it is called the natural base, which we express with the letter E. So this number, the natural base, Euler's number, is represented by the letter E. And it is equal to the following. Write this down. 2.71, 82, 81, 8. Let me double check. I think it's 846 after this. Where's my packet? Here it is. 82, 81, 8. 1 second. 82, 81, 82, 846. So there should be a 2 right here, and then 846. And now this is what's going to happen. I'm not going to keep going. I'm going to put 3 dots. Now, who can tell me what you think these 3 dots represent? What does it mean when I write 3 dots? It keeps going forever. It means it does not stop going. Like, it's just going to keep going forever and ever. Obviously, I'm not going to spend my time writing out all the numbers because there actually is no limit. It just goes on forever. Now, here is some fancy mathematical notation for you guys. So, what we're saying is that the letter E, the number E, the natural base, is the following. It's equal to the following. as we compound the interest infinitely many times. That's what it means. The limit as n goes to infinity means as we compound the interest infinitely many times, our balance, that's what this equation represents, our balance in the bank will be equal to the number 2.718281, etc., etc. Okay, that's what we're saying. Okay, 2.7182, etc. Now, like I said, this number is called Euler's number. It is also known as the natural base. Now, we have explored irrational numbers in the past. Maybe you don't remember this, but you have explored pi. The number pi, 3.141592, so on and so forth, is an irrational number because it goes on forever. So when something cannot be expressed as a fraction and also has no pattern, meaning it just goes on forever, that is what becomes an irrational number. This is different from other numbers like imaginary numbers. For example, an imaginary number would be like the square root of -1. We have established that the square root of -1 doesn't exist because you can't take the square root of a negative number. However, we make it work because if we didn't have imaginary numbers, then math wouldn't work. So like we make up, these things just so that math can essentially work for us. So anyway, these are numbers. Sorry, pi and e are also called transcendental numbers, and this just means the same thing. These are numbers that don't have a pattern, go on forever, and are part of the algebraic sets of numbers. Okay. All right. So here's the next thing. We have explored exponential growth and decay. Formula for compound interest is something that we've also seen. Now this is the new material, the formula for compounded continuously. The word continuously means infinitely many times. Okay, that's what it means. What I want you to do real quick is to look at the difference between these functions. So we have an a that's common, but there seems to be something here that was replaced. And what I want you guys to see is that the equation here, 1 plus r over n to the n, is replaced by the letter e, by the number e, right? Because we said that if we compound the interest infinitely many times, we're just going to get 2.7182. Okay? All right. Another thing I want to make you guys aware of is that these functions are the same. What I mean is it doesn't matter if you see little a or capital P. They represent the same thing. Okay? They represent the principal or the initial investment. Okay? All right. So here's your next task. You're going to go ahead and turn to the person next to you, and you're going to do this with them. You're going to figure out which formula to use. Now, I'm going to do one for you so that you understand what my expectations are, so that we don't have to redo this activity, or I don't have to re-explain it. But what you're going to do is you're going to read the paragraph, and then you're going to figure out which of the 3 formulas you're going to use, and then you're actually going to write an equation. For example, a dog has 10 fleas living in its fur. Suppose the number of fleas increases at a rate of 20% per day. So we're going to write an equation that could be used to predict the number of fleas in the dog's fur. Now, of the words that I highlighted, in this entire paragraph, there is no compound interest because the words compound are not in here. So that means that I am not going to use compound interest or compound continuously. So I'm only using one of these 3. Now, the word increase is telling me that, hey, this is going to be growth. So I'm going to use the exponential growth formula. That'll be f of t. We start with 10 fleas, and this is increasing at a rate of 20% per day. And so we're going to get, essentially, we're going to get this following formula, 10 parentheses 1 plus 0.2 to the t. So does that make sense how I want you guys to do this? You're going to identify which formula best suits the scenario, and then you're actually going to write an equation. I'll label this E and G. EG for exponential growth, just so you guys know what it would be. All right, so take about 5 minutes to go ahead and work on the next 3 questions. Go ahead and get. Okay, so let's take a look at the following. Penelope invested $1,000 in risky cryptocurrency. Suppose that the currency decreases at a rate of 14%. Write an equation. Okay, which equation did we use here? Which of the 3 from the top? James, which of the 3 from the top did we use? Yes. Very good. This is exponential decay. And what would that look like? Rebecca, what is the formula here? We have, what is the initial amount of money? 1,000 parentheses 1. Because it's decay, 1 minus, what's the rate? 14% is what as a decimal? 0.14 to the power of t. Excellent. Okay. Next one. Sammy deposits $3,000 into a bank that offers 1.65 annual interest compounded quarterly. This is an example, obviously, of compound interest. Now, what will the equation actually look like? Let me hear from the following person. James Carpenter. Go ahead. Number 3. Hold on. Not 0.032. 0.0165 over what? Go ahead. Over 4 to the what power? 4t power. Excellent. Okay, and then let's finalize with the last one. Lauren deposits 10 grand into a bank that offers 2.31 annual interest compounded continuously. Write an equation that could be used to predict the amount of money in the bank. So this one will look like what? Marco, what will this look like? 10,000 E to the what power? Excellent. So 10,000 E to the 0.0231 T. All right, excellent. Good job, you guys. Let's move on to the next 2 problems, and that'll be it. I will give you guys your break after that, and then you guys will have an appointment book to take care of with those around you. Okay. All right. So let's see if you can figure this out. This should be pretty easy. But E, the number E, is known as the natural base. What do we think the logarithm will be called that is the inverse of the natural base? What will the logarithm be called? If it's the natural base, then it should be the what logarithm? I keep emphasizing this word. If it's the natural base, then it's the what logarithm? I heard it here. It's the natural logarithm. Okay? So anytime you see a logarithm with base e, that is called the natural logarithm. It only makes sense because base e is the natural base. So natural base, natural logarithm. And the thing is, you won't see it written as log base e of x. Instead, you will see it as ln. ln of x. And ln of x means natural logarithm, except the letters are switched. So L comes first, logarithm, n natural. I believe it was done this way because the mathematician that came up with this, it was probably like a different language. It was probably like Latin or something, or maybe Spanish. So L, logaritmo, N, natural, right? That's why we have those letters come first. Okay? Now, let's look at 2 example problems that I think should set you up for what we're going to see in the appointment book. So make sure you're paying attention. This is like the key section of the notes. So make sure that you are listening and writing stuff down as we go through it. So I'm going to read the following problem to you. Chloe deposits $3,000 into a bank that gives 2.4% annual interest, compounded continuously. How much money will she have in 4 years if she does not make any deposits or withdrawals? All right. So I'm going to call on some people right now. Just help me out with what you think is important from this paragraph that I should highlight. So what is one thing that I should highlight from this word problem? Lily. Say that again. 3,000, which is the deposit amount. Okay, let's look at another thing. Let's go with Callie. Go ahead. So 2.4% interest. There should be a few more things here that we should highlight, other important aspects of this. So Eric, let me hear from Eric. 4 years, so that will be the timestamp of 4 years. And I believe there's still more. There's two more things that we should be able to highlight from this. Will, give me another thing, please. Round to the nearest cent. And finally, we're missing just one last thing. David, let's see if you can catch this. Compounded continuously. So all of these things that we're highlighting, these are essential key words that are going to let us know how we're going to solve the problem. Now, because we're using we see the words compounded continuously, that means we're using the formula for compounding continuously. So let's go ahead and write it down. It is the PERT formula, so A of t equals P e to the RT, where P stands for principal, so that is your initial amount of money. That's the initial investment. E is the natural base that we've just found. R is going to be your rate, and T will be that timestamp or that time interval. Okay. So let's replace the following variable or the following values within the variables where they go. All right. So I should have the following: P is equal to what? P is equal to what? To 3,000. So I have 3,000 e to the power of, now 2.4% is a percentage. We need to convert this to a decimal. What would that look like as a decimal? You're from Jackie. What would 2.4% look like as a decimal? 0.024. Now, we do have a value of time. We want to figure out how much money we're getting after how much time? 4 years. So we're going to replace the value of t with 4. And this is what we're going to plug into the calculator. Now, I have not shown you guys how to do this in the calculator yet. So I'm going to need you to look up here while I show you on the screen on how we're going to do this. So first off, please turn on your calculator if it's not already on. And make sure that you're looking to the screen so that I can show you where you will find the value of E. All right. So you should have nothing in your calculator. Now, we want to type in the equation 3000E. So you're going to type in 3000 first. 3000. Now, to find the natural base on your calculator, you're going to go to the button here that says ln. But you will notice that e to the x is in blue. So what that means is you need to hit the second button first, and then you can hit the ln button. And so if you did it correctly, you should have 3000 followed by e and then an empty box in the exponent space. There you will fill in the interest rate, which is 0.024. Parentheses 4. So you should have the following. You should have the following argument. And if you did this correctly, you should get 3,302.277. Give me a thumbs up if you see this number on your screen. Excellent. Write that number. However, we're going to round to the nearest cent. So let's go ahead and do that. 3,302 point. What will it become if it's 0.277? What will it become as nearest cent? 2.8 or 0.28. Sorry. Okay. So this is how much money we should expect in the bank after 4 years. All right, seems easy enough. Now, we're going to do one more example, and then we'll have you guys just take your break, or we'll give you guys your break. This next section will be a little challenging, so like I said, make sure you're following along. I'm going to go ahead and read the word problem, and we're going to do the same thing. We're going to analyze the important things here. Kim deposits $5 million into a bank that gives 1.3% interest compounded continuously. How long will it take for her to have $7 million in her bank account? All right, let's go ahead and highlight the important information here. What is one thing that I should highlight? I'm going to have you guys raise your hand for this. What is one thing that you believe is important here that I should highlight? James. Compounded continuously is one thing. There's still a lot more, so let's keep getting some ideas up here. What's the second thing that I should highlight? Natalie. 1.83%. We still have a few more things to highlight. What's another thing that is important here that I should highlight? DeMarco. 5 million. What else is important here? 7 million. There's one more thing that is important here that we should highlight. Nearest tenth of a year. So rounding, the rounding aspects. We're rounding to the nearest tenth of a year. Okay, let's go ahead and write our equation first. So we're starting with, once again, A of t equals PERT, P-E-R-T. Principal is 5 million. 5 million. Oops. 5 million E to the RT. What is R? In this case, R is 0.0183 and T. Now, this is a key part which I forgot to highlight, but how long will it take is another very important thing that you have to consider. Whenever you see the words, how long will it take, that means we don't know what T is. That means we have to algebraically solve for T. Okay? So, we have this equation, 5 million E to the 0.0183 T, and we're going to set this equal to how much money we are looking to have in the bank. How much do we want in the bank? 7 million. So we're going to set the following up. 7 million equal to 5 million E to the 0.0183 T. Like I said, when we see the words, how long will it take? That means we don't know what T is. We have to algebraically solve for T. And to do algebraically means you have to divide, multiply, do a bunch of other stuff, right? So how will I get T alone? What do you think my first step should be based on the setup that I have? What is the first thing going to be? Am I going to subtract 5 million? Does that seem right? No, I cannot subtract it. I must divide it. So I'm going to divide both sides by 5 million. And because 7 million and 5 million have the same number of zeros, I could get rid of the zeros and just rewrite this as 7 over 5. Right, I'm just simplifying that. And all of that's going to equal E to the 0.0183 T. This is where we run into the next step. If we are currently in exponential form, what form must I switch into to try and get T by itself? Log form, logarithm. However, because this is the natural base, then I'm not going to use a regular logarithm. I'm going to use what logarithm? The natural logarithm ln. So I'm going to get the following statement. ln of 7 over 5 equals 0.0183 T. However, T is not by itself yet. We still need one final step. And what will that final step be? I mean, yeah, calculator, but there's like a final step to get T by itself. What's in front of the T? What number is in front of the T? Okay, tell me what decimal is in front of T. 0.0183. So we must divide both sides by 0.0183. And so that's how we'll be able to get our solution. Okay? All right, I'm going to show you on the calculator how to do this because you're going to have to do it in steps, okay? All right. So everybody look up here. First thing you want to do is you're going to hit the LN key. LN, so that you have this open. LN of 7 over 5. Hit enter. You're going to get this massive number. Or not massive, I guess this is really small. But there's a lot of numbers in it, that's what I meant. And you're going to divide this by 0.0183. And if you did this right, you should get the following. 18.386. Give me a thumbs up if you see 18.386 in your calculator. That means you did it correctly. Okay, so that is the solution. We're going to go back and write it out. Let's not forget, the final sentence says round to the nearest what? 10th of a year. So 18.386 will round to 18 point what? 18, not 18.3, but 18.4. And let's not forget the units. Are we talking about minutes, months, days, years? It's going to take 18.4 years before this person sees their investment go from 5 million to 7 million. Okay. All right. Are there any questions with the two questions that we've just looked at? All right, then we're going to go ahead and take a break. When we come back, we'll work on the appointment book.